Welcome to homework.
So first we set the free body diagram. Now assuming the ladder is just about to slip, so the frictional force will be the static frictional force. Therefore this will be equal to the static friction times the normal force Fn. Now as you can see, the ladder is of length L, and this means that d2 will be equal to, so L is, as you can see, this triangle, L is the length of the hypotenuse. So D2, which is the side opposite to theta, will be equal to L sine theta. Sorry, D2 will be equal to, D2 is this length. I think I have, let me just correct that. So D2 is this length, and since this length from this point to this point is 3/4 of L, therefore D2 will be 3/4 of L times sine theta. Similarly, D1 will be L over 2 times sine theta, and D3, which is this length, will be equal to L times cos theta. Now since the ladder is in equilibrium, so we write the horizontal and vertical equations of Newton's law and set them to 0 because the ladder is in equilibrium. And we also have this frictional friction condition that we will be using later. Also, we need to use the torque equation, and we are taking the torque about this point where the ladder is resting on the ground. Let's first write the vertical forces, the horizontal forces. So we have Fgx minus Fw, which is this force, to be equal to 0. So this gives Fgx, the force from the ground, the horizontal component of the force from the ground. So that is equal to Fw. For vertical component, we have Fgy going upward minus small mg minus capital Mg equal to 0. From here we can find Fgy equal to m plus capital M times g. And if we calculate the torques about this point, we have, and consider the clockwise torques to be positive, so we have a torque from small mg. So we take small mg times d1. We have another clockwise torque due to capital Mg. Then we have another torque due to Fw, which is counterclockwise. So this is the torque due to Fw. So from here we can find Fw, which is equal to mg d1 plus capital Mg d2 over d3. Let me just put all the forces that we found in boxes. Now, if you compare this frictional force and Fn to this diagram, you'll see that Fgx is in fact the friction force, and Fn, which is the normal force from the ground, is Fgy. Basically, the ground component, the perpendicular component of the force from the ground, is the normal force, and the horizontal component of the force on the ladder from the ground is the friction force. So if we plug these two over here, we find what is sorry. So if we plug these two over here, we find F gx to be equal to mu times Fgy, and Fgx is Fw. So let me box this equation as well. Now we have four equations: 1, 2, let me just call this 2, 3, and 4. Now now we want to find this coefficient mu, the coefficient of static friction. So let me move to the next page. So from equation 2, we can write mu s to be equal to Fgx over Fgy. Now for Fgx, we will use Fw, and for Fgy, we will use equation 3. So this will be equal to Fw over m plus capital M times g. Now for Fw, we will use equation 4. So for that, let me just write that down. So Fw, we calculated this force to be equal to this value, and in the denominator we have Fgy, or the normal force. Now plugging the values of small m, capital M, d1, d2, and d3, we get mu s to be equal to half of m plus 3 over 4 capital M over small m plus capital M times tan theta. So basically, if you substitute values for d1, d2, and d3, the term L, which is length of the ladder, will cancel out from the numerator and denominator, and also g, the acceleration due to gravity, will also cancel out. And finally, you will arrive at this expression for mu s. Now you can simply substitute the values for small m, capital M, and theta, and find mu s, which comes out to be 0.257.